I've got an A+ in my Physics 2 course, and here's how you ace your final exam. You don't need to read the entire textbook, you just need to know these 6 concepts. Disclaimer: watch this video with your own judgment. If your professor recommends something, then it's probably going to be more important and it might show up on your final exam. So use that as your priority.
I'll be discussing 6 concepts plus a bonus one in the end. Let's begin with the first concept, the RL circuit.
Let's say we have an LR circuit just like this, with a battery attached to it. We apply Kirchhoff's loop rule, which states the sum of EMF in the circuit is equal to 0. In the beginning, when the current I equals to 0, the change of current is at its maximum, which is E over L. But at steady state, when the change of current is equal to 0, we have I equal to E over R. We rearrange this above equation to get this particular equation. After solving and integrating, we get I equals to E over R times 1 minus E raised to minus R over LT. When we plot this over a graph, our graph will look something like this. This reaches an asymptote and the maximum value of E over R. But let's say we remove this battery, then this equation changes to this equation, and subsequently our graph will look like this. An additional piece of information is when tau equals to the time constant equals to L over R. It's somewhere around here.
Faraday's law and Lenz's law.
Imagine that we have an area with magnetic field lines passing through it. The magnetic flux is equal to the line integral of the magnetic field times the dA, which is this cross-sectional area, which is BA cos theta. This is known as Faraday's law. Lenz's law is derived from Faraday's law, which states the direction of magnetic induction is opposite to the cause of effect. To explain this, let's say we have an area with magnetic field lines passing through it. After some time, the magnetic field lines kept increasing. To determine the direction of EMF, we curl our fingers opposite the direction of the increasing magnetic field, and the thumb points towards the direction of the EMF, which is like this. The equation of the EMF is given by this equation.
Let's talk about electric potential.
Let's say you are a positively charged particle, and your friend is also a positively charged particle. Both of you face a force that is repelling each other, so it'll push you away from each other. This force is represented by this equation, which is 1 over 4 pi epsilon naught q1 q2 over r square. However, the lines of force that can be visualized between you and your friend is represented by what is known as the electric field. The electric field is given by E equals to F over Q, which is also equals to this equation. Now if you were a positive charge, the electric field lines would be away from you. And if you were a negative charge, the electric field lines will be coming towards you.
Moving on, we have electric fields and electric forces.
Let's consider you and your friend again. Now because of the force between you, you know that there is a potential energy that exists that prevents you from joining each other. The electric potential energy that exists between you two is given by this equation, which is 1 over 4 pi epsilon naught q1 q2 over r. However, when you want to consider just the electric potential, it is represented by this equation, V equals to U potential energy over Q, which is nothing but 1 over 4 pi epsilon naught Q over R.
At number 5, we have application of Gauss's law.
This concept comes directly from Gauss's law. Gauss's law states that the electric flux in a closed area is equals to the charge enclosed over the epsilon naught. Let's say you have a conducting sphere. The conducting sphere has charge that goes towards the surface of the sphere. If you consider a region inside the sphere, the charge enclosed is going to be equal to 0, since all the charges are towards the surface. This would mean that the flux will be equal to 0. This would also mean that the electric field inside the sphere is going to be 0. But now, let's say you have an insulating sphere. The insulating sphere will have charge not moving anywhere and staying inside the sphere. The charge enclosed is going to be represented by the charge density times the volume of the enclosed sphere. Let us say we depict this on the graph. For the conducting sphere, the electric field stays zero until we reach the radius of the sphere, and then it starts to decrease because the electric field is given by this equation outside the sphere. But let's say you have an insulating sphere. The graph of this, the electric field starts slowly going towards the maximum value at R and then starts to decrease as you progress forward. This is because when the radius of the inner circle is less than the outer circle, the electric field is given by this equation. But outside the sphere, it is given by this equation. Before we move to the next concept, I would like for you to comment below to tell me which concept do you find more difficult, and I will explain to you in the replies or make a video altogether. Let's see.
The LRC series circuit with an alternating voltage source.
Let's say we have an LRC circuit with an alternating source voltage. We are concerned with the impedance and the phase angle. For the impedance, we use Kirchhoff's loop rule. The voltage of the inductor is IXL, the voltage of the resistor is IR, and the voltage of the capacitor is IXC. XL is measured by omega L, and XC is measured by 1 over omega C. We plug all of these values into the impedance equation, which is square root of R square plus XL minus XC whole square. Substituting the value of XL and XC, we get this equation. For the phase angle, we need the phasor diagram. We have the capacitor voltage leading by 90 degrees, and we have the inductor voltage lagging by 90 degrees. This would give the resultant V vector, and the angle between V and VR is the phase angle. We can calculate the phase angle using this equation, and when we substitute the values of XL and XC, we get this equation. And now for the bonus topic.
Energy and momentum in electromagnetic waves.
Let us consider an electromagnetic wave. The total energy density is given by this equation. This is the energy density of the electric field, and this is the energy density of the magnetic field. To further simplify this equation, we're going to use this relation, and we're going to use this relation. This relates electric field and magnetic field, and this is a relation for speed of the electromagnetic waves. The epsilon 0 and mu 0 are nothing but electric constant and magnetic constant. The equation for energy density further gets simplified into this equation, which is equals to epsilon naught E square. But we're concerned with the change in energy density, which is given by this equation. This helps us find the Poynting vector, which is nothing but change of energy density over unit area. The Poynting vector is given by this equation, which upon simplifying is going to give you this equation from above equation. Other forms of the Poynting vector equation are these, which is also equals to EB over mu naught. The average value of the Poynting vector is the highest value divided by 2. This is also known as the intensity, which is I.